Hello everybody, this is for the AWC's Chem 151 Quiz 4 review and mid-semester review. I'm Lily McNair and I'm the Supplemental Instructor for General Chemistry 1 at AWC. So what we're doing today is we're looking at solubility and concentration, and here we have our solubility curve. And what the solubility curve tells us is the grams of solute per 100 grams of water. And it can tell us if a solution is saturated, supersaturated, or unsaturated. And when we talk about saturation, we're not talking about the molecular structure. We're actually talking about in a solution, how many grams does it have? Enough grams that to be saturated, or does it have not enough or too much? And we can use this to find what things have a higher solubility, or just the solubility at a given temperature. As temperature increases, we can see that molecules have different solubilities. And again, this is just the unit that we're in, grams of solute per 100 grams of water. It could change depending on the solubility curve you have. Now, the first thing that we're going to do is we're going to look at, does potassium chloride or potassium chlorate have a higher solubility at 60 degrees Celsius? So we're going to look then at 60 degrees Celsius right here. And we look at potassium chloride right there, and potassium chlorate, KClO3, potassium chloride, KCl. So let me see if I can darken these in a little bit for you. And we know how to name these from naming molecular compounds. And so at 60 degrees Celsius, we look here, we're going to plot it for KClO3. It's about 28 grams per 100 grams. 28 grams of solute per 100 grams of the solvent water. KCl, it's a little higher. It's maybe 39. And so we're going to say that potassium chloride has a higher solubility at 60 degrees Celsius because we see that the solute level is higher at the 60 degree mark. So then the next question is, what is the solubility in milligrams per 100 grams of water of ammonium chloride at 343 Kelvin? Well, the first thing that we're going to do is we're going to say 343 minus 273, this is Kelvin, is equal to 70 degrees Celsius. There's our temperature conversion. Okay, then we're going to look at NH4Cl right here. It's this purple curve at 70 degrees Celsius. And we see that it's at about 62 grams per 100 grams. And this is NH4Cl per 100 grams of water. And then we're going to multiply this grams, the 62 grams, so that we have it in milligrams. So that becomes 62,000 milligrams per 100 grams of water. 62,000 milligrams of NH4Cl ammonium chloride per 100 grams of water. And we know that because there's 1,000 milligrams in a gram. Now we're going to see, I wrote that in the wrong place, sorry. So this is actually up here, 62,000 milligrams NH4Cl per 100 grams of water. So let's ignore this part for now. So now we go to the next question. Which compound has the greater increase in solubility per unit of temperature increase? So going over to our solubility curve, we're going to see the ones that go up are the ones that are increasing as we move along in temperature. We have the biggest one is this KNO3, potassium nitrate. Right here, we see the steepest increase. So then we know, so let me get rid of this really quick. Then we know that this is KNO3, and let me just write up here 62 grams per 100 grams. That's how we got this. Okay, so KNO3 has the greatest increase in solubility. Then the next thing we're going to look at is which compounds have an inverse relationship between temperature and solubility. A direct relationship would say as temperature increases, solubility increases. So what we want to see is as temperature increases, solubility decreases for an inverse relationship. And we see that's true for three. That's SO2, HCl, and NH3. All three of these have curves going down. This is HCl. You may not be able to see it that well. Okay. Next, we're going to describe saturated, unsaturated, and supersaturated. Saturated is the max or maximum amount of solute completely dissolved in a solution. It's going to be at the line. It is the line. Unsaturated is the amount of solute below the maximum amount completely dissolved in a solution. I'm not going to write that all out though. This is going to be below line, below maximum, below saturation. And supersaturated is the amount of solute above saturation. And again, this is going to now be above the line. So let's use this information to answer these next two questions. Is 80 grams of KCl per 100 grams of water at 343 Kelvin saturated, unsaturated, or supersaturated? We already know that 343 Kelvin is 70 degrees Celsius. Let's then find our KCl. KCl is right here. At 70 degrees Celsius, its saturation point is about 45 grams of solute per 100 grams of water. So then 80 grams of KCl per 100 grams of water is going to be supersaturated. The next question is 30 grams of KCl per 50 grams of water at 343 Kelvin. So this time though, we have to take 30 grams of KCl per 50 grams of water and multiply it to our 100 grams, or else we can't use the curve if it's not 100 grams. We know that this is multiplied times 2, so we do the same up here, and we have 60 grams of KCl per 100 grams of water. We've already gone and seen that this is at about 45, so this one is also supersaturated. Now for our final question about nitroglycerin, we have this molecule, which is nitroglycerin, and is administered to patients with angina pectoris to relieve ischemia to heart tissue by acting as a vasodilator. The question asks if an EMT administers 3 doses, and I'm sorry, this is a typo, this should be 0.4 milligrams, to a patient with a blood volume of 4.9 liters. What is the concentration of nitroglycerin, parts per million, parts per billion, and molarity after 1 dose? Okay, let's look at the 1 dose. So we can find first that through counting, we have a carbon here, and we have 2 hydrogens here, 1 hydrogen here, 2 hydrogens there, that our molecular formula is C3H5N3O9. Using that information, our molar mass is 227.11 grams per mole. Okay, so this is just our information that we're going to use, but we don't need right now. Because parts per million is milligrams per liter. So we take this 0.4 milligrams, we divide it by 4.9 liters, and the answer that we get, 0.082 parts per million, is the answer to the question. Simple as that, milligrams per liter. Parts per billion is micrograms per liter. Now there's 1,000 micrograms and 1 milligram. So if we multiply 0.4 milligrams times 1,000, we get 400 micrograms, and we divide it by our same liters, and we get 81.63 parts per billion. This is after 1 dose. Now for molarity, molarity is moles per liter. And so we're actually going to use the 0.4 milligrams, and we're going to convert it to grams first. So we say 0.4 milligrams times 1 gram over 1,000 milligrams is equal to 0.004 grams. Then we take this and divide it by our molar mass to 227.11 grams per mole. This way we have our grams canceling out, and 0.004, so that's 3 zeros, 4, divided by 227.11 grams. We get, this is equal to 1.76 times 10 to the negative 6 moles. Now we take that information and we put it up here, 1.76 times 10 to the negative 6 moles for solute, divided by 4.9 liters, and we get 3.59 times 10 to the negative 7 big M moles per liter. Okay. Now after 3 doses, all we need to do is multiply this times 3. Okay. And so what we get is, once this is multiplied times 3, we get, so that's 0.082 times 3, 0.0246 ppm. This is after 3 doses. Same thing for here. So that's 81.63 times 3. We get 244.89 ppb. And then over here, we'll take that, let me put it down here, 303.59 times 10 to the negative 7 molarity times 3. And we get 1.078 times 10 to the negative 6 molarity. And this is after 3 doses. And so that's this page about solubility and concentration for the Quiz 4 review and mid-semester review as well.